Screencast 18.4, Energy and Spontaneity. When we consider chemical processes, we can see how sometimes they occur very rapidly. We can see how sometimes they might occur very exothermically. We can see how sometimes they don't seem to go to completion because they tend to go forward as well as backward. In this case, we are considering whether a reaction will take place spontaneously with no outside help under the reaction conditions that might be given for any particular system. Lots of things happen spontaneously. Consider, for example, waterfall running downhill. That's a spontaneous process. Nothing's going to stop that. A lump of sugar will spontaneously dissolve in a cup of coffee. Water will freeze at the right temperature. Heat will flow to the cooler substance if they're in contact, for example. A gas expands in an evacuated system. It'll just spread out. All these things happen, and all you got to do is watch. Iron will rust under the right conditions. Now let's think about that. If one of these is true, what else? If it's true that a reaction is spontaneous, what does it say about the rate of that reaction? Will it be rapid? Will it reverse itself? What can we say about equilibrium? What can we say about exothermicity? Does it require an exothermic reaction to be spontaneous? Well, here's some data. A spontaneous reaction might be the combustion of methane. Look at that. It's an exothermic reaction. No surprise there. We can make water from its ions, and that also is an exothermic process. It's also spontaneous. So I suppose it's always true, but here is an endothermic process. Water melting. And this will happen spontaneously under the right conditions. Also, ammonium nitrate will decompose in the presence of water, and this is also an endothermic process. So, does an exothermic reaction imply spontaneity? No, there is not a guaranteed relationship. Let's do one more slide and talk about where this came from. Josiah Willard Gibbs, who grew up in New Haven, came up with the idea of a way to measure spontaneity, and he used these terms. This is known as the free energy equation. It says delta G equals delta H minus T delta S. This is Gibbs' free energy. This is the enthalpy, meaning the heat at constant pressure. And if we subtract the entropy times the temperature, we will have Gibbs' free energy overall. Free energy is a measure of spontaneity. If it's negative, it implies a spontaneous process. Entropy is basically a measure of randomness, and as it increases, it becomes more positive. And enthalpy, as we said before, is heat at constant pressure. So when it's negative, there you go. You got a spontaneous process. So let's take another look at entropy, a deeper look at entropy, in the next slide. This is Screencast 18.4.